Hello, everyone. Okay, right. Let's do this. Inferential statistics. Um, Arguably, from a student point of view, one of the hardest parts of the entire spec, if not the hardest part of the entire spec. Students don't get this. They really struggle with the idea of significance and inferential statistics. So I'm going to try slow this down as much as I can and go through it. I think this will be a very useful video going forward. What do we mean by inferential statistics to begin with? So there's two types of statistics that you need to know. You need to know descriptive statistics and inferential statistics. Descriptive statistics are pretty much a lot more basic. They are mean, median, mode, range, and standard deviation. And they merely just describe the data. They're just telling you what the data is about. They try to express what the data is showing, but they're relatively basic. So that's descriptive statistics. When it comes to inferential statistics, though, we're talking about much, much, much more complex statistics, and this is where we're talking about statistical testing, and statistical analysis. And this is where it does get a lot more complex. So this video is focused on the latter, in this case, inferential statistics. These slides are largely split into two. The first half is us going to be looking at what we mean by inferential statistics and significance, bit of probability in there. And the latter slides are looking at the harder part of it, which is interpreting and picking the right stats test. So there are parts of this slide that I will go through quite quickly. There are parts of the slide I will skip over, but there are also parts I will spend quite a bit of time on. So this question down the bottom here is actually quite an important quite an important starting point. Is there any possible chance that Ash's findings with conformity, or Milgram's findings with obedience, or Ainsworth's findings with attachment styles, is there any chance that their findings have got nothing to do with obedience or child rearing patterns, and that what they found were complete freak findings? Is there a chance that 65% of Milgram's study, is there a chance that he just accidentally picked the most obedient sample around? Is there a chance that his findings are complete freak findings, and that if we were to do them again, we wouldn't find that? There's always a chance. There is always a chance. So this is why you cannot say the word prove in psychology, because to say that Milgram proved his hypothesis correct would be to say that Milgram was 100%. That's what happened. That's not necessarily true. Milgram, every single experiment always has a small chance of being a complete freak finding that would not be found again. I'm very sorry. I'm very sniffly. I'm just getting over a cold at the time of filming, and my nose has decided to unblock itself at the start of this video. So when we're looking at statistics, a psychologist has to do all of this, right? They have to conduct the investigations, collect the data, and then at the end of it, they have to confidently reject or accept an alternate or a null hypothesis, right? So this is, if you want to go down the psychology route, you do need to be good at stats. You absolutely need to be good at stats, or you need to understand how to do statistics. And if we're just looking at this, eyeballing this data here, right? If you were just to look at this, you got the silent condition, you've got rock music, and this is reaction times. And as you can see, silence, the reaction times are significantly faster than that of rock music. Now, do you just go, oh, brilliant, we found a difference, right? No, you don't. You have to do significant statistical testing, and you have to find out whether you have significance. So what I'm just trying to say here is researchers don't just look at their data and just decide they found a significant difference. They need to put all their data through a statistical test to see what are the chances that they've actually found significantly different findings. That's quite an important bit, so maybe rewind maybe 10 or 15 seconds. Oh my God, what's wrong with me? I've got a COVID face mask here. This is my new handkerchief. So, need to remember to throw that away. So you don't, as I say, you don't just eyeball the data and decide, I found a significant difference. You have to put all of your data through a statistical test to see if you have significance. But Kieran, what is significance? That's a very good question, lovely viewer. This is pretty much what I've said already. Once a study's been carried out and the results collected, the next stage is to decide what hypothesis to accept and reject. Do you accept the alternative hypothesis and reject the null, or do you do vice versa? And you don't just decide whether to accept or reject it. We put our data through to see if what we have found is a genuine difference if you're doing an experiment, or a genuine relationship if you're doing a correlation. And what is the chance? So this is really the key bit here. Let's say statistically, Milgram found he was 95% sure that the obedience was caused by the experimenter. Statistically, statistically, he is 95% sure. The statistics are telling him we are 95% sure that that's what caused the obedience. That means there is a 5% chance that the obedience was down to what we call chance factors. Again, that's quite an important factor, so maybe go back a minute if you want to try and wrap your head around it. But if you are 95% sure you have found a genuine difference, i.e. the IV has had an impact on the two DVs, if you're 95% sure, that means that you are 5% sure that the factors came down to what we call chance factors. Now, if you do a stats test, and the stats, and I'll come back to the stats in a second, later on when we do critical values. But if you do a stats test and it basically tells you we are at least 95% sure the IV was affected the DV, that's what we call significant findings, and that's what we mean by significance. I'll repeat that again. Significance is essentially when we are at least 95% sure that it was actually the IV that affected the DV, and it wasn't down to some chance factors. Now, you have to be at least 95% sure statistically. Statistically, you have to be 95% sure. The stats test has to tell you we are at least 95% sure that the IV in this case was what affected the DV. If you're a 94% sure, you have not achieved significant findings. And that is the threshold for all psychology. Your aim is to achieve a 95% confidence that it was the IV and not some other extraneous or confounding variable that actually affected the DV. And it's this that leads to significant results, significant findings. And that is what all researchers are after, is significant results. So let's just have a look at this example just here. This is, I think it's a memory test of some kind. So imagine we conducted we conducted an experiment into the effects of traffic noise on memory reasoning. In this case, traffic noise is clearly the IV. You've got high noise there, you've got low noise there. And in this case, we're clearly measuring the DV, which is memory reasoning, which let's say is out of 20, right? Out of 20. We've got a hypothesis here. But if you're looking at the data down the bottom, the rough data, you can clearly see that there was a difference, right? In this case, people scored higher in the memory test than in the low noise than they did in the high noise. But again, you can't just eyeball the data and figure that out. You cannot say just by looking at the scores that there's a significant difference. In this case, you're going to have to do a stats test. Essentially. So, probability, right? This is where probability comes in. I'm not going to spend too long on this, but as you may know from your maths days at school, or maybe college, if you, for some reason, took maths at college, that probability runs between 0 and 1. 0 is it is not possible, it's not going to happen. 1 is it will happen, it must happen, right? And generally speaking, nothing is 1. Nothing is 1 and nothing is 0, right? Purely, right? Nothing is 1 and nothing is 0. So if we were to say you will think about elephants later today, as in, beyond the next hour, you're probably looking at, I don't know, like a 0.1 and 0.2 chance of that actually happening. So level of significance, you need to know what the P stands for, because you have to write about the different confidences, which I'll go into in a second. So when we're writing P, we're talking about the probability that the results occurred due to chance. The reason why I say this is because this down here is what you need to know. So when we have P, in this case, P, and write this down, is the probability that the results occurred due to chance. So in this case, remember we said psychologists look for a probability of 5% or less that what they think is the IV effect and the DV was actually down to chance. So Milgram, remember, is 5% or less sure that what he found was he's 5% sure that his findings were a complete freak finding, and that has got nothing to do with the IV whatsoever. Same with Ash, right? They're at least 5% sure. Let me be clear about this. If Milgram or Ash were less than 95% sure the IV affected the DV, we wouldn't be talking about them right now. So statistically, they are very, very confident, at least 95%, that it was actually the IV that did affect the DV. So in this case, what this means is, and remember what the P means? The P means the probability that results are down to chance. This is equal to or less than 5%. And that is how you write 5%, 0.05. 0.5 is 50%. So, can we make sure we are writing this down? So P 0.05 is we are sure the probability that the results occur due to chance is less than 5 or lower than 5%. So, a couple of bits here, not too bothered. That is significance, right? You may have to watch that one or two times. Slightly repetitive things I'm saying, but essentially, what I want you to take away from this is, in order for you to get what we call significant results, you statistically need to be 95% sure that it was actually the IV that affected the DV. And if you're 95% sure the IV affected the DV, there's also a little part of you, in this case 5% or lower, that actually thinks it could be down to chance. So not to get too confusing here, but if I find 20 pieces of research that all believe the IV did affect the DV, right, like Ash, Milgram, Zimbardo, they're all 95% sure. One of them is a complete freak finding. So it could be Milgram. I'll say that again just because I think students don't necessarily take it in the first time. If Milgram is 95% sure that the IV affected the DV, that means 5% is 1 in 20. Right? So if I got 20 pieces of research that all believe they found that the IV affected the DV, and statistically they all believe that, one of them, the researcher and the test believe the IV did affect the DV, but it's actually a complete freak finding. This is why you have to repeat your studies over and over again to try and achieve reliability. Because if Milgram is 95% sure, if I were to do it again and we find the same findings, that increases your confidence. But again, less on that. The second part, and probably the harder part here, is the statistical test part. Now, you do not need to know how to do all of these stats tests. The only stats test you need to know how to do from start to end is the sign test, and I'm going to be doing a separate video on that. Super easy, by the way. It's almost embarrassingly easy. The other ones, including the sign test as well, you do not have to know how to do. as in you do not have to know how to do the stats test, but you do have to be able to interpret the data. You do have to be able to interpret the data. Now, let me just go through this, because this is where it gets quite complicated, and I want to try and nail this video. I'm sorry about my crudeness here, but the basic point of all stats tests is for you to put in loads of numbers into the stats test, into a database, loads of numbers packed full of them. I've seen sheets and sheets of data before, like going into a stats test. And the whole point about a stats test, this is so important, is that it craps out one number. That number is called the observed value. You're definitely going to need to know that in the next 5 minutes. So the number that it craps out, 4.31, whatever, it can be literally any number, 4.31, that number, I don't know why I'm holding this number like a baby, that number is what we call the observed value. You then take that observed value and compare it off to another number to see if you've got significance, which I'll go into in a second. But that is the basic point of all stats tests. Now, before we get into that whole bit, I just want to go through what the stats tests are. You need to know the main thing you need to know is what stats test do you pick? What stats test do you pick? Now, in order for you to do this, you need to know a few other things. So, different stats tests can be used. You need to be able to pick the correct one. In the exam, you're going to be asked to decide what stats test you should use, and you're going to be able to explain why. So far, this goes up to 7 marks. I do believe AQA are going to stretch it to 9 marks soon. So these questions are quite important, and they're asking them at the time of recording. AQA are asking these questions almost every single paper because they know the students don't know it. And so they're just pummeling them. Stats. Stats used to be worth only about 4 marks out of the 288 marks. But now it's hitting something like between 20 and 25, a lot more basically. So how do you pick the right stats test? Kieran, just get to the point. Picking the right stats test is dependent on 3 things, and you need to know and be able to identify these 3 things. The first one is the type of data collected: ordinal, interval, or nominal. This is known as what level of measurement you are doing. Now, I think there should be another video on levels of measurement. Double check the site, Research Methods 1, 2, and 3. Double check those. It probably is going to be Research Methods 3, but double check that. If not, then email me and I can make it. So you need to know what the level of measurement is. You need to know what the experimental design is, or the correlational design is. So you need to know whether it's matched pairs or independent measures or repeated measures. Maybe you need to know whether it's a correlation. And the last thing you need to know is whether the test is a test of difference or whether it's a test of a relationship. It's a test of difference if it's an experiment, because the whole point about experiment is you're testing for a difference between the DVs. It's a test of a relationship if it's a correlation. Now, if you've got all 3 of those, you need to know this test. You just do. You just need to know this test. You just need to know this table. You need to be able to remember it. So down the left-hand side, we've got nominal, ordinal, interval. You need to know the order of those, by the way. NOI, right? You need to know that. Up the top, we've got independent measures and repeated measures, and these come under the umbrella of a test of difference, because remember, what did I say about test of difference? It's about experiment. Independent measures is done in experiments, and repeated measures is also done in experiments. So if you identify, by the way, that it's independent measures or it's repeated measures, it's also a test of difference. And over the other side, you've got a correlation, and obviously this is a test of a relationship. Now, and that is, by the way, all 3 of those. We got type of data, we got experimental design, we got test of difference or relationship, and this is it. You got test of difference or relationship there. You've got experimental design, and then you've got the level of measurement there as well. If, for example, you identify that they're doing an experiment, therefore it's a test of difference, you see in the stem that it says, it won't say it's repeated measures, but you figure out that it's repeated measures. and that actually it's an ordinal type of data, then what you would say is, oh, therefore it's a Wilcoxon test. And you would have to explain it's a test of difference because it's a repeated measures because all participants did condition A and then all participants did condition B, and you'd say it's an ordinal data because it can be ranked. So that is a very, very common question. Sometimes they say the experimenter did a Spearman's row. Well, 3 reasons would you use to do a Spearman's row and contextualize it to the study? And that would be worth 6 marks. So in this case, you'd say, well, a Spearman's row is a correlation, and we can see it's a correlation because blah, blah, blah. It's a test of a relationship, and we can see it's a test of a relationship because in this correlation they did blah, blah, blah. And it's also ordinal data because the data is rankable, and we can see this from the stem because blah, blah, blah. You need to be able to do this. My advice is some students take a risk and they learn this very, very late. It's a stupid idea. You need to come up with some sort of mnemonic for you to be able to wrap your head around. This is one my student come up with a few years ago. I'm going to apologize in advance because it is very weird, but it's a mnemonic and it helps me remember it. A Chinese man lost his sight, and couldn't find his wife Whitney. Instead, he bumped into his friend Will Coxon, and they shared a spearmint. At first, they were unrelated. Then they became related and had a pair of sons. Don't really know what that means, to be honest with you. But it helps me remember. It helps me remember the order of it. Come up with your own one, and trust me, you will not lose this. Now, let's just raise it to the last level of difficulty. Do you remember I said to you that you need to know that a stats test basically craps out one number, and you then take this one number called the observed value, and then you will compare it to the right part of the critical values table. This is also something you need to know. Once we have done all the stats tests, once we calculate value, call that the observed value. To be honest, I don't want to confuse calculator for critical, but just ignore that bit there. Right, it's called the observed value because you observe it in the data. We then need to use the critical values table to tell us whether or not a result is statistically significant. Now, critical values table is basic. I've got loads here. They are basically tables full of numbers, right? So this one just here is for the sign test. If I turn it around, this one right here is for the chi-squared, and it's basically just a list of numbers. And now you need to pick the right place. Sorry, I wasn't meaning to do that. I don't know why. Sorry, I used something else. You need to find the right place to find out, and compare your observed value to the critical value in this case. And I'll go through why in a second. You do not need to revise these numbers. They will give you all the numbers you need in the exam. Now, here is a good example. Here is a good example here. Right now, let's just imagine I've done a sign test. Right, I think I've shown you. You got the sign test stuff. You got the sign test critical values right here. They're on the board. They're on the screen in front of you. I don't want to go into too much detail, but you do need to know N quite a lot of the time. N is basically the number of participants. So on a critical values table down the side, you've usually got, not on all of them, but you've usually got N down the side. Now, one thing you need to know is how many people were in the study. And that takes you down to here, which means we're looking down this line somewhere, right? But we also need to know what line we're looking at here. So one thing you have to work out is whether it's a one-tailed or a two-tailed test, right? And you'll be given the information in the STEM, right? Now, they're not going to tell you, oh, it was a one-tailed test, but they may say something like, oh, previous research found. And remember, if there's previous research found, you tend to do a directional hypothesis. A directional hypothesis is also known as one-tailed test. Again, I know I'm starting to go quite fast, and it may be worth just going back and watching it again, but everything I'm saying is making sense to me, so therefore it should be making sense to you. Let's just imagine this experiment that needed a sign test used a directional hypothesis. So do you remember what I said about what level you go to? You need to figure out what level you go to here. So basically, which of these is 5%? Which of these numbers that I'm circling is 5%? Is it that one there? Is it that one there? Is it that one there? I'll give you a second to have a guess. Right? If you're guessing here, then you're wrong, right? It's actually this one just here. So in this case, we're looking down this column, and we've already established we're looking at the line of 17. So in this case, oh, and by the way, the one thing I'll come to that in a second. But remember, I told you the whole point about the stats test is that it craps out one number, right? In this case, that number is 3. The S, I should say, is, not to get too confusing here, but each stats test has an observed value, but each stats test calls it something different. For the sign test in this case, S is the number that gets crapped out. I'm sorry to be so crude, but S is the number that gets crapped out of the sign test. So all the data got put in the sign test, blah, 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 blah. And it was this number that came. This is the observed value. You have to compare this observed value with whatever number comes up. And in this case, it was this number down here. Why is it this number? Just as a recap, well, N is 17. So we need to go down to 17 because that was the number of participants that were in the study. And we had to go to the right part of this bit here. That was 0.5. That takes us to 4. So hold on a second. We've got an observed value of 3. S equals 3, just there. We've got a critical value of 4. And you have to compare those two numbers together. But there's always, and this is one of the most important parts, you need to look at the rule of every stats test. Down the bottom of every stats test is the rule. And you can see that just on here. This one here says the calculated S, so this just here. So basically, for us to have significant findings, for us to be at least 95% sure, the calculated S must be equal to or lower than the critical value table that you come up. So my question to you is 3 equal to or less than 4? Yes, it is. Therefore, in this imaginary stats test, we are at least 95% sure that it was the IB that affected the DV. Now, I fully appreciate you may have to watch that a couple of times to wrap your head around it. This is one of the hardest parts of the spec, and if you've got that first time, then I think it's safe to say you are naturally academically talented. It will take a lot of you multiple views to watch that, and that's perfectly okay. I don't expect you to have this first time round. I will briefly do something on type 1 and type 2 errors, but I'm not going to spend too long on this because this would probably be another thing. But it is possible that sometimes we make errors when we decide whether or not to reject the null hypothesis. That being said, by the way, remember, going back to this one just here, if we have found significant findings, we will accept the alternative hypothesis and we would reject the null hypothesis. If S was 5, right, just imagine S was 5, and I went down here and 5 is more than 4, we would have then found non-significant findings, right? Because remember, the calculated S has to be equal to or less than the critical value for you to have significance. If it's more, we don't. So a type 1 error is when we accidentally reject the null hypothesis when we should have actually accepted the alternative hypothesis. I had a bit of a zoning out moment then. Type 1 error is when we reject the null hypothesis when we should have rejected the alternative hypothesis. So it's known as a false positive. So, for example, we think we have found that the IV did affect the DV, when actually statistically we weren't actually that sure. So it's a mistake that it's called a type 1 error. A type 2 error is the opposite way round. It's a false negative. That's when we accept the null hypothesis. So we say the IV didn't affect the DV when it actually did. So there's not really much more you need to know for type 1 and type 2 errors beyond that. But this is the sort of thing that we are looking for, by the way. I'm not going to spend too long going on this, but this is a typical STEM that you're going to get. A psychologist, and I want you to be able to read this, and I'm going to read it out to you because, why not? And I want to know whether or not you could come up with what stats test it is. I'd be very impressed if you could. A psychologist wanted to test whether listening to music improves running performance. The psychologist conducted a study using 10 volunteers from a local gym, and the psychologist used a repeated measures design. That's a big clue there, by the way, repeated measures design. So you've just narrowed, if you're clever, you've just cut out 5 stats tests. You've narrowed it down to 3 in this case. Why have you narrowed it down to 3? I'll go back. Because it just said they've done repeated measures, which means it's one of these, right? And it's not this, and it's not these. All participants were asked to run 400 meters as fast as they could on the treadmill in the psychology department. The psychologist recorded their running times in seconds. So what you now need to decide is whether this is nominal data, ordinal data, or interval data. If you can't decide that, so what exactly are they measuring in this case? What are they measuring? They're measuring running times in seconds. Is that categorical? If it is, it's nominal. Is it rankable? If it is, it's ordinal. Can you rank running times in seconds? Yes, you can. Does it have a true zero? Because remember, ordinal has a true zero. Let me ask you, can you run 400 meters in under 0 seconds? No. Therefore, running time in seconds has a true zero, has a starting point. Interval data does not have a starting point. So in this case, what we are clearly dealing with here is a Wilcoxon test. It's repeated measures. It's a test of difference because it's an experiment. It's ordinal data because you're using rankable data that you're using for your DV, and therefore this test is a Wilcoxon test. And you'd have to be able to describe that. Now, I appreciate what I've gone through is incredibly complex. It probably will take you 1 or 2 watches. I will try add chapters to it to make it easy, but this is a hard part of the spec. But trust me when I say this, you are 100% going to need to know what to pick, what stats test to pick for any situation. I cannot lay it out clearer than that. Watch this a couple of times. I think it might be quite useful. But if not, we will be going through this in lesson quite a lot. Maybe come up with your own mnemonic. But that is everything for inferential statistics. And as I believe it, that's everything for research methods 2 done. I hope it was useful.